Collector feedback bias connects the base resistor to the collector instead of directly to the supply. This simple change makes the base drive respond automatically when collector current changes in this lesson. We derive the DC equations, locate the Q point, examine sensitivity to beta, and verify practical operating limits. By the end, you should be able to explain the negative feedback sequence, derive the base loop and output loop equations, calculate the quiescent current and voltage, and verify forward active operation. You should also be able to predict how beta variation moves the Q point. In fixed bias, base drive is almost independent of the collector voltage. So a change in beta can produce a large change in collector current. Collector feedback bias connects the base resistor to the collector node. The base current therefore responds to collector voltage movement, creating negative feedback and reducing the resulting Q point shift. Suppose collector current tends to increase, the voltage drop across the collector resistor rises, so collector voltage falls. Because the base resistor is connected to the collector, this lower collector voltage reduces base current. The reduced base current opposes the original increase in collector current. That opposing action is negative feedback. This is the practical collector feedback amplifier used in the first worked example. The feedback resistor runs from collector to base. The collector and emitter resistors establish voltage drops determined by current. For steady DC analysis, every coupling or bypass capacitor is replaced by an open circuit, leaving only the supply resistors and transistor. Before writing equations, simplify the circuit correctly. Capacitors are open at DC steady state, not short circuits. Retain the supply, collector resistor, feedback resistor, emitter resistor, and transistor. We use a constant silicon base emitter drop of about 0.7 volts and test the active rebound assumption after finding the Q point. At the collector node, current through R sub C divides into collector current and base current. Therefore, the exact resistor current is I sub C prime equal to I sub C plus I sub B. Since base current is normally much smaller, we often approximate I sub C prime by I sub C state. This approximation rather than silently treating the two currents as identical. The base emitter loop begins at the supply, passes through the collector resistor, the feedback resistor, the base emitter junction, and the emitter resistor, then returns to the supply. The current labels matter. R sub C carries I sub C prime, R sub F carries base current, and R sub E carries emitter current. Apply Kirchhoff's voltage law around the base emitter loop. The supply rise equals the drops across the collector resistor, feedback resistor, base emitter junction, and emitter resistor. This expression retains the correct currents in each branch and is the starting point for either approximate or refined hand analysis. For the usual hand calculation, approximate the collector resistor current by collector current. In forward active operation, collector current equals beta times base current and emitter current is approximately collector current. Substituting these relations converts the loop equation into one unknown base current. After substitution, collect all base current terms. The feedback resistor appears directly, while the collector and emitter resistances are multiplied by beta. This reflected resistance is the reason collector feedback reduces beta sensitivity. part of the denominator grows with beta instead of remaining fixed. A refined hand calculation retains base current in both collector resistor and emitter current expressions. Then I sub C prime and I sub E each equal beta plus 1 times base current. The resulting denominator contains beta plus 1 multiplying the sum of collector and emitter resistances. For large beta, this differs only slightly from the approximate expression. To determine collector-emitter voltage, use the output loop through the supply, collector resistor, transistor, and emitter resistor. Physically, R sub C and R sub E share the available supply voltage with the transistor. As collector current rises, the resistor drops increase and the remaining collector-emitter voltage decreases. Using I sub C prime approximately equal to I sub C and emitter current approximately equal to collector current, the two resistor drops combine. Rearranging Kirchhoff's voltage law gives collector-emitter voltage as the supply minus collector current times the sum of collector and emitter resistances. For the first example, the supply is 10 volts, the feedback resistor is 250 kilo ohms, the collector resistor is 4.7 kilo ohms, and the emitter resistor is 1.2 kilo ohms. Beta is 90 and the base emitter drop is 0.7 volts. We will calculate base current, collector current, and collector emitter voltage. Substitute the numerical values into the base current expression. The sum of collector and emitter resistances is 5.9 kilo ohms. Multiplying this by beta and adding the feedback resistance produces the total effective denominator. The resulting base current is approximately 11.91 microamperes. Collector current follows directly from the forward active relation. Multiply the base current by beta. 90 times 11.91 microamperes gives approximately 1.07 milliamperes. This is the quiescent collector current. Use the output loop equation with the calculated collector current. The collector and emitter resistors together are 5.9 kilo ohms, giving a collector-emitter voltage of approximately 3.69 volts. Both Q point coordinates are positive and the voltage is comfortably above a typical saturation value, so active region operation is reasonable. Rewrite the collector current equation by dividing the denominator by beta. The result contains R sub F divided by beta plus the resistor sum R prime. If the resistor sum is much larger than R sub F over beta, the beta dependent term has little influence. Collector current then approaches V prime divided by R prime. Repeat the calculation with beta increase from 90 to 135. Although beta rises by 50%, collector current rises only from 1.07 to 1.20 milliamperes, about 12.1%. Collector-emitter voltage falls because the increased current creates larger resistor drops. Feedback reduces but does not remove Q point movement. A nominal Q point is only the beginning of design verification. Leave enough distance from cutoff and saturation for the expected signal swing. Check resistor and transistor power dissipation. Repeat the DC calculation at minimum and maximum beta and across temperature. The feedback resistor also loads the collector node, affecting AC gain and input resistance. Avoid 5 recurring errors. Remember that the collector resistor actually carries collector plus base current. Include both collector and emitter resistances in the reflected term. Open capacitors for DC analysis. Continue from base current to collector current and collector emitter voltage. Then verify the operating region. Finally, describe feedback as reducing beta sensitivity, not eliminating it. Collector feedback bias stabilizes the Q point by making the base current respond oppositely to collector current changes. The approximate base current equation contains beta multiplying the collector plus emitter resistance, which reduces sensitivity to beta. Always calculate the complete Q point, verify the operating region, and finish with power, tolerance, and temperature checks.